So let's go through our derivation to create our 3D Hooke's law relationship. So I'll take you back probably to a testing lab that you may have had. So this looks similar here. We've got a specimen, and we're going to take note of the axes. In this case, X is along the length of the member, Y and Z are in the transverse direction. So the specimen has some initial length. We use L naught, right? It's got some cross-sectional area. That's an A sitting there. And so this specimen with the axes specified has an initial state of stress in the X direction. It's going to be P over A, where the internal axial force is going to be equal to the applied external load. All right, and that may be measured by a load cell. And so we're putting ourselves in a testing laboratory here. We've got free surfaces Y and Z. We have no constraint, no loads, no kinematic restraints, so our stress is X, Y, and Z. So sigma YY, sigma ZZ are equal to 0. So you pull on this specimen, right, or apply a load, and you end up with elongation that's occurring due to the tension that's being applied. And so that results in an axial strain epsilon XX. And that's calculation-wise, that would be change in length divided by the original length. So you may have a strain gauge that's telling you this. Right, we've got in the perpendicular directions, right, you see the dashed original size, and now you've got some elongated and shrunk contraction in the perpendicular directions. And so we'll account for that here in just a moment. So if we look, what that strain in the X direction is going to equal the stress in the X direction divided by Young's modulus. So we've got some other terms that are going to show up. This is going to be in the linear range of the material. We're going to deal with materials that are isotropic, so they react the same or behave the same in all directions. So if we just kind of shuffle this around, you might see something that is familiar where stress is equal to E times strain. But we're going to keep it back here in the strain relationship, or calculating strains in terms of stress divided by E. And so in the perpendicular directions, we have strains. We have strains Y, epsilon YY. We have strain epsilon ZZ. And that comes through Poisson's ratio. And Poisson's ratio is defined as the negative value of the lateral strain divided by the axial strain. So there's a negative sign right here because one of these strains, either this one or this one, is going to be negative. The other one's going to have to be positive. So this specimen has two lateral axes, right, relative to the axial direction. So for this one, X is in the axial, Y and Z are both lateral. So that's going to tell us that we can calculate that strain. So Poisson's ratio, right, is equal to the negative of epsilon YY divided by epsilon XX. So if we just plug in for those values, solving epsilon YY, and then go ahead and just plug in the value for epsilon XX, there would be our calculation for the strain in the Y direction. So this tells us that stress in the X direction creates a strain in the Y direction. Exact same thing happens in the Z direction. So using lateral strain as the Z direction, we're going to do exactly the same thing. Shuffle epsilon ZZ, and there's our calculation for strain in the Z direction. So just our summary, that with only a stress state with stress in the X direction, letting sigma YY, sigma ZZ equals 0, we end up with strains, both direct strain, epsilon XX, and we end up with also lateral strains. So this is going to go a little bit quickly. We're going to take that exact same specimen, except the only thing we've done is shuffle the axes. So I'm going to put Y along the length of the member. That leaves Z and X in the lateral direction. And so here's our state of stress. Right? Sigma YY is now equal to P over A. Sigma XX and ZZ are equal to 0, so there's our stress tensor. And this is going to go quickly. So now epsilon YY is the axial strain, which is equal to sigma YY divided by Young's modulus. Using the definition of Poisson's ratio, we can go ahead and calculate the lateral strains. So we would end up with exactly the same presentation, except now a strain in the x direction is caused by sigma YY, right? A contraction. And so again, there's some tension and compression here, right? To have this all work out, tension needs to be positive. So tension in the YY direction is going to create contraction in the x direction. Exact same thing happens over in the ZZ direction, or the Z direction strain is going to be negative with a positive sigma YY. And so we would just shuffle our axes and put the Z axis along the length of the member, therefore having a sigma ZZ. And we'd end up with, we would get strain in the Z direction now would be the direct strain because we've got sigma ZZ applied. All other stresses are equal to 0. And we would have contraction in x and y through Poisson's ratio. Again, when I say contraction, that would be from tension in sigma ZZ. So we've quickly gone through uniaxial in all three directions. And so we just ask ourselves, what creates strain in the x direction? So we're just going to fish out the answers that come from sigma XX, sigma YY, and sigma ZZ. So we're about to use superposition here. So the same thing we're going to do for epsilon YY and epsilon ZZ. So the summary of all this looks like three terms. I'm going to have for epsilon XX, there's the direct stress. And I'm also going to have answers for sigma YY and ZZ. So I'm going to have three stresses that contribute to strain in the x direction, axial strain. All right, it looks very similar for the y direction. All right, again, noticing signs here. All right, we have the positive term coming from the direct stress. We've got negative terms coming from stresses in the perpendicular directions. So there's our three strains, which are each contributed by three different stresses. Problems that we'd run into this week extend into biaxial, and those would be problems where two normal stresses have values. And we'll also run into strain gauge problems. So we're going to always just, we will start from the understanding that a strain in a certain direction can be caused by any three normal stresses, not just one, which is probably where you started your conversation, where back in the testing lab, this was in a uniaxial case, we would have those two stresses equal to 0. So that's where the sigma equals E times strain came from. So we kind of want to think a little bit more general, and this is only a very specialized case. So moving from normal stresses to shear stresses, let's go ahead and take an element. We'll apply a force F across the top, and so we end up with a shear stress, which would be equal to F divided by A. That would be the average shear stress calculated, right? A little different than the VQ over IT, but that's a calculation for the shear stress, would just be the force divided by the area. And so that creates a shape distortion, but there is no volumetric change when this occurs. So this type of shear is called direct or simple shear. And so the element distorts, and we're going to call the angle of distortion. That's going to be gamma, which is the shear strain. So from a stress-strain relationship, or the constitution, we would end up with the shear stress is equal to G, which is the modulus of rigidity, or the shear modulus, multiplied by the shear strain. So there's our stress-strain relationship. So instead of Young's modulus, we end up with the shear modulus. And so sigma xy, right, shear stress, produces shear strain, but nothing else. So we end up with three relationships. So there's nothing similar to a Poisson effect that occurs. So when we rotate this, when we rotate the axes, there's nothing else to trace. So we end up with shear strain is produced by shear stress. So all I've done is just rotated, sort of solved in terms of shear strain. So this is strain to stress. So taking a look at the differential element with the stresses applied. So if we have an element with shear stress, so looking at the axes, this would be a sigma yx. On this face, we'd have a sigma xy. For this element to be in equilibrium, it's going to require that sigma yx equals sigma xy. If it wasn't, then this element would be spinning. So something's in static equilibrium. This is going to have to be the case that the shear stresses on adjacent faces have to be equal. So that's why we talk about where heads have to touch heads or tails would touch tails. So in relation to that requirement, what we're going to do is take that angle gamma and we're going to rotate it halfway. And so we end up with an angle gamma over 2, an angle gamma over 2, and we're going to call that epsilon xy or epsilon yx. So this shows up on your equation sheet, and I'll show you where in just a moment. So here's our kind of summary, is that the shear strain comes from the shear stress divided by the modulus of rigidity. Those two have to be equal to each other, and those shear strains, gammas, are equal to twice epsilon xy. So the epsilon xy is going to be sigma xy divided by 2g. So we're going to put all that together. We would have epsilon xz and yz related to the shear stress. We know that those epsilons have to be equal to each other. xy has to be equal to yx. And so in matrix form, we've got two representations. We've got strains expressed in terms of stresses, which is how we've derived it for the most part. If we were to pre-multiply each side by the E matrix, we would end up with stresses in terms of strains. So on your equation sheet, they're sitting right here. So this would be the epsilons are equal to, this is the inverse of the E matrix. Over here would be the stress vector. So looking in here, we see a lot of 1 over E's. There's Poisson's ratio. There's modulus of rigidity. There's our G. We'll end up deriving this, that there's a relationship between G, E, and Poisson's ratio. Slide over here, we would end up with the same relationship, but this is stresses in terms of strains. This is called Lemay's constant, and so you see that over up here in the upper left quadrant, which is where the direct stresses relate to the direct strains. So let me point out where those gammas are as well. You start to see them down here in the torsional bars. So there's gamma, there's the kinematics of it. And over here in the constitution, there is shear stress, which is equal to G times gamma. If we shuffle that around, it would be gamma is equal to sigma divided by G. Right? And again, you see that a couple different places. That would also be a shear stress.